Okay, so it is time to start today's Grease Thief Boot Camp Asia. And welcome. My name is Rich Wurzbach. I'm with MRG Labs, and we are the developers of the Grease Thief. And today we're going to be talking about, we're going to get things kicked off today, which is an opening session. It's going to be an overview about this 3-day workshop that'll be happening over the next 3 days, starting right now with session 1. Each day will consist of 3 sessions. We have them spaced through the day. Gives you a chance to take a break and catch up on things, and then come back and join us and learn what we can about grease sampling, grease analysis, greasing in general, auto lubers, good practices for selecting grease, determining how much grease to add, and really covering grease at a level that we rarely get the opportunity to see. So that's what we're covering. So I want to start with this overview of the schedule, and just let you know that everyone that's joining us now through the YouTube live streaming capability, you'll be able to participate in this first session, this overview session. And then those who have enrolled in the class using the link that you see here, the store.mrgcorp.com, and enrolling there will be able to have their own login ID and password to participate in the remaining 8 sessions over the next 3 days. And so that's going to get us started here today. So I'm going to get us into our presentation and load that up for you here next. Okay. So again, we've put this training together and tried to make it convenient for our friends around the world. And we're in the Americas. Our organization is based in the U.S. and in the state of Pennsylvania. And it's not always very convenient to reach out to folks in different parts of the world. So we've scheduled this for your convenience, and I hope that works out well. So the let's see here, the kind of the course background and where this came from is there's a couple of inputs here. One was part of an effort I did for the Electric Power Research Institute, or EPRI, called the Effective Grease Practices Guideline, which we researched and published to the electric power industry, and a workshop that was developed as a result of that. And you'll see some reference to some of the work that was done there that was really meant to cover all aspects of grease lubrication, to develop an optimal grease lubrication strategy for asset owners. Part of the course has been developed over time with our experiences in biomedical research and pharmaceutical manufacturing, the nuclear power industry. You'll see references to wind turbines, which is a significant area of interest around greasing and grease analysis and grease optimization. We're going to draw from some reliability programs that have been developed in the pharma industry, and some projects in wind and nuclear as well. We'll talk about the setup, calibration, and operation of the Grease Thief Analyzer, and we're bringing that to the forefront here and making it one of the topics of discussion, as it has begun to change the industry approach to grease analysis. It's really the first laboratory instrument designed solely around effective analysis of grease samples, which are at their heart much different than oil samples in their behavior, the way they're handled, the way we make measurements. And so this recognizes those differences and looks at ways to optimize both the sampling process and the analysis that we can do with those samples. And then there's, I'm going to demonstrate some things with sampling kits. We're going to have hands-on analysis. Well, we're doing this remote, so not everybody can get their hands on the equipment. Those who have the analyzer will be able to follow along. But Richard Janoski, the lab manager for MRG Labs, will be joining us tomorrow to do some hands-on in the second session scheduled for tomorrow. So that gives you a bit of the background, the topics that we're going to be covering over the next 3 days. And over the next hour and a half here, I'm going to go through some selected sections of this material to kind of give you a sense for what we can expect going forward. So in this course, the outline, our objectives here, we're going to talk about greasing practices, how you go about selecting the right grease for the application. And that goes to really it starts with understanding the machine. What kind of machine is it? And what are its requirements? And how do we select a grease that's going to work in that specific application? And it's not something that has been done effectively in a lot of instances. It's something that often gets overlooked. That perhaps there's an assumption that any grease gets the job done. And we're going to talk about the steps that goes into making that determination. We'll talk about grease delivery technologies. And this is going to be both manual and automatic methods for doing so. I'll talk a little bit about some evaluation of grease test stands, and that being some studies that were done as a part of this effort. So I'm seeing a message come through now that folks are asking if the event has started, and so I'm going to just take a moment to make sure that people do have access and respond to some of those messages, because I want to make sure everyone gets an opportunity to participate. There we go. Okay. And yeah, so we've got the evaluation of the grease test stands. And really what these test stands have done, we're trying to challenge some of the assumptions that have been held about grease analysis. Challenge and see what's really happening, because grease is a bit of a mystery, right? We have perhaps a grease gun and we pump that into the machine and we just assume everything happens that needs to happen to deliver that grease and to move it where it needs to be and get the old grease out of the way and so forth. Some of these test stands were designed specifically to answer these kind of questions, like where does the grease go? Where do I need to go to get a representative sample if I want to take a sample of that grease? How does grease purge out of a drain on a piece of equipment? We can understand about oil that we open a plug and gravity allows that oil to drain out, but not so much with grease. So how does grease move around in a machine? And some of these test stands helped us answer some of those questions and give us a lot of insight about grease behavior. So I'll share what some of that was. We'll talk about grease sampling. Number one, how do you start? Like, how do you decide where the grease is in the machine and how do we get to it? And then how do you use some of the standards and procedures that are out there about taking representative grease samples? How do we leverage things like ASTM standard D7718 to understand, what tools should I use? How do I use them? How do I access? What are the pitfalls? What are the possible interferences with collecting a good sample? And so we'll talk about those things as well as demonstrate some of them. We'll talk about sample handling and preservation. How do you get the sample? How do you transfer it? How do you make sure that the sample that you take is in the right condition and presented in the right way for the purpose of analysis? We'll talk about laboratory analysis. We'll both talk about the specialized equipment that exists for grease analysis, and also how we try to use, in many cases, existing instrumentation for oil analysis, but use it in the right way to get a good, repeatable, trendable picture of the condition of the grease. It isn't always as simple as pushing or shoving or pressing the grease into whatever is normally an oil analysis process. It often involves some important handling steps to get that analysis correct. We'll talk about how we initialize the instrument, get it set up, get it prepared for analysis, and then also calibration. And again, a lot of this is going to about the instrumentation itself is going to be with some hands-on demonstrators we broadcast from our laboratory with lab manager Richard Janoski. And then we'll run some tests. And then I think what's really important to a lot of people is about analyzing the results. So what does it mean? When you get a number from a grease test, what does it mean? How do you use it? How do you leverage that to understand the condition of the grease and the condition of the equipment that's being tested? And so we'll spend some time understanding that, and also from that, understanding the value of grease analysis. Why do we spend the time and the resources it takes to get the sample and analyze it? What can we gain from doing so? What are the benefits of that? And we'll talk about, we'll spend some time talking about case studies and the cost benefits of doing grease analysis. So here's what you can expect to see happen over the next few days when you sign up for the full Grease Thief Boot Camp at the link that I gave you earlier. And however you got invited to this, whether it was through the LinkedIn event schedule or a direct email, you should have a link to go to the registration site at the MRG website to sign up for the remaining sessions here. But let's take some time now and give you the benefit of going through this and giving you kind of a preview and an overview, really, of what to expect. And so at the start of this, it's all about greasing practices, right? It's about what should we be using, and is the grease we're using really the right thing? There's a few questions that we need to answer to know what grease to use, or if we're already using a grease, is it the right one for that application? And that first and fundamental question is about viscosity. And really, this is often completely overlooked when it comes to greases. Oftentimes, I have folks that will say, we're using grease in this machine. Well, what kind of grease it is? Oh, it's a lithium number 2. And that's the end of the discussion. Okay. In other words, that we know we wanted to use some kind of lithium grease and that it needs to be a number 2. Well, this has nothing to do with, nor does it answer any questions about the viscosity of that application. And that is the fundamental and first question that needs to be answered. Is the viscosity of the base oil that's in this grease the right viscosity to protect that bearing, to protect those gears, and so on? If it's a rolling element bearing, which a lot of times that's what we're using grease for, is rolling element bearings, ball bearings, cylindrical bearings, spherical roller bearings. In order to properly protect those, we're relying on an elasto-hydrodynamic film, and that is directly related to the viscosity for the application. So in the same way that we would never take an oil to lubricate a bearing and say, well, I'm not concerned about the viscosity, I just want to know what kind of oil it is. We would never do that. We would always ensure that we had selected the right viscosity. So when it comes to greases, we have to select that right viscosity in order to expect good performance of the machinery. And so that becomes question number 1. And then how do we go about calculating that? Number 2, what is the optimum viscosity for the bearing at operating temperature. And this goes to understanding a little bit about how that machine is being operated, what its operating conditions are, what kind of ambient environment it is in, and so on. But really, a lot of times, this is where we're reliant on the designer or the manufacturer of the machine, of the asset, to understand what that operating temperature is, or within some range. And other times it's a combination of that, and also our awareness of how we are operating it. Are we operating it per the design? Are we subjecting it to different operating conditions? Are we running it at speeds different than it is designed for? It sounds unusual, but anymore we see the use of variable frequency drives. And variable frequency drives allow the asset owner to change the speed to make it go faster or slower. And often the manufacturer has designed the machine for its maximum speed. And so when you see the selection of a lubricant, it's often based on that maximum speed. And if we're going to be operating the asset at a different operating speed, perhaps at different operating temperatures, perhaps there's cooling involved, and we supply cooling water that's higher or lower than expected. All these things can change that operating temperature. But finding that out is really important, because that's what sets the optimum, or the operating viscosity for the bearing when it's in operation. So that's the next thing we figure out. And then we what is the viscosity of the lubricant that we selected at that temperature, and does it meet that? And then we look at this pitch line velocity, which is the speed, or it's sometimes called the speed factor, or the NDM, which is the rotational speed in RPMs times the mean diameter of the bearing, or the average diameter. And that's really that angular velocity, or the pitch line velocity of the rolling elements. And is it low enough that grease can be an effective long-term approach? Sometimes grease is the wrong lubricant to use. And for very large, very high-speed bearings, that could be the case, where really only oil is going to be able to effectively lubricate that. So understanding the application, understanding the machine is important in deciding that, because if it's too high, the grease may be flung out of the bearing, or be disturbed, if you will, or sheared down so that it no longer functions as a grease. So these things go into that selection process, these kinds of questions. In addition to, like this picture shows here, the NLGI grade. Yeah, the NLGI grade is important, and it helps the grease stay in place, but it's not the only parameter that's important for greases. It's one, but it's not the only one. And so, all these other things factor into that as well. There's some other tools out there that we can use to help make these determinations. This happens to be one that I've used on a number of jobs, and it's this kind of circular calculator where you can kind of dial in your application, knowing what the bearing bore size is, or the inner diameter, and how that relates to the speed. We can move the center section around, and that becomes a function of what the speed of that is. And then it not only does it help us understand the volume, or the amount of grease that should be added each time we add grease, but also how often. And that has to do with the size and the speed of the bearing, but it also has to do with the environmental factors and other things that affect grease life. Things like the ambient temperature, things like the moisture and particulate contamination that's in the environment. Because one of the things that drives greasing practices is the presence of contaminants. In other words, in the environment that the bearing is in, contaminants are trying to get in. They're trying to work their way in to the working parts of that bearing and get in through the grease, where they can do damage. Moisture can impact the formation of that lubricating film. Particulate can get under the elements and become a source of abrasion or fatigue. And so grease becomes a tool to keep them away. So we pump grease in and push those out. How often we have to do that is really dictated by how dirty that environment is and how frequently we need to push that back. So that goes into that calculation. And then things like the orientation of the bearing. Is it kind of horizontal, so everything kind of stays in the housing, stays in contact with the bearings? Or is it vertical, where you have this up and down arrangement of your shaft and gravity is constantly pulling that, or trying to pull that grease out of the away from the bearing? And so we got to push the grease back in more often. So all these things go into determining that optimal frequency. The geometry of the bearing tells us how much to add. And together, when we can work all these things out, we get some guidance on where we should be starting with our lubrication practices. Now, it's not the end of the process. Some folks are familiar with ultrasound as a tool, where ultrasound can be used to listen to the bearing and to hear if those if that lubricating film has been established or not. Because if it's not, more ultrasound is given off. It's very noisy. We can hear that with the ultrasonic detector and know that more grease needs to be added. So we can make adjustments to these calculated frequencies by getting feedback from a tool like ultrasound or vibration. But another thing that we can do is look at the grease sample itself and use that to help us understand if we have an optimal lubrication condition. And so we'll talk about that, the grease analysis as a tool to optimize lubrication. To start with these calculations of what should be a starting point for greasing quantities, greasing amounts, and so on. But then using grease analysis to get feedback to say, is that really dialed in where it should be? Am I greasing too often? Am I not greasing enough? Am I allowing contaminants to get in and become damaging to the equipment so that the machine won't last as long, as that its fatigue life is diminished, that we see wear, abnormal wear, and finally failure? So these are all things that we're going to look at and learn more about in this course. I really like this flow chart that we put together as part of this guide for the Effective Grease Practices Guide for the Power Industry, because it walks you through this process of grease selection. And, to take away something from this is that, if you've worked in an environment where you're responsible for grease selection, you may say, well, it's pretty simple. You just grab that grease gun and you pump it in the machine. But when you see a chart like this, it becomes apparent that it's a lot more complex, or it should be more complex of a decision to make sure that the grease that you're using is correct. Okay, so we can, start this process out here at the upper left. And, does the machine require circulation cooling? Does it require filtration? Or does the machine specify oil lubrication? And if it does, we're done with this chart. In other words, we got to be open-minded to the idea that not all machines are optimally greased for their lubrication. Some machines won't work well if grease is used. And so that should really be the starting point. Should it be a greased machine? And then we can walk through this process and say, are there other technologies? Should the grease be lubed for life? Should it be sealed or shielded in a way where we never add grease and we just have the kind of grease that can last a long time? And then you can walk down through this whole, kind of process of doing calculations. Part of it is you check with the OEM, the original equipment manufacturer, and see what information they provide about their machine. Sometimes it's quite detailed and quite targeted and obviously quite good. Other times it's not. The details aren't there. It's very vague. It doesn't even address the viscosity. And so we may need to go deeper in those cases. And one more thing to talk about on this topic is about, how do we determine those amounts and those frequencies? And so this is where you'll see the next few slides in the presentation as we go through the course in the coming days, get down into the nitty-gritty of this process of calculating, selecting, and then being able to utilize all this guidance that might be out there for grease lubrication. So the next thing I want to talk about here is about auto lubers. Okay, so this is another thing that we, and let me just back up here one spot. Yeah, is auto lubers. So we've got the option of manually lubricating our equipment, and often machines will have a small hydraulic, or what they call Zerk fitting, that allows you to put a grease gun on and then pump that grease in there until we deliver the right amount. But in other cases, that's not the best approach. Maybe it's hard to get to these locations. It could be that the amount of grease or the frequency is so great, we'd be constantly running out there to pump grease in. So we take advantage of some of these devices that are available that do the greasing for us. And they are spring driven. There's maybe a spring that pushes down the grease slowly over time. There are gas driven styles where there is, we can kind of start a process, and there's this slow creation of gas pressure from typically a chemical process. And that gas pressure pushes that grease out slowly over time to replenish grease and add new grease. And that can be very effective and cost effective as well. And then there's electromechanical devices, which use typically some kind of battery power and positive displacement, perhaps a screw mechanism that's slowly advancing certain amount of grease at some frequency that it can be programmed for. And there's some differences here in what the features are, how much pressure they can generate, where the cost levels are for these different devices. And it's good to be able to go through this process. So we do that in this workshop, talk about these level of details. Start out by talking and comparing some of these things. Like the top one here is one of these spring-loaded auto lubers that I talked about. The one in the bottom is a cutaway cross-section that lets you see inside one of these gas powered units, where to the left of the picture you have a little space where the gas or the chemical reaction takes place, and the gas expands, and that expansion of the gas pushes the piston forward, forcing the grease out of this unit and into the bearing. And so there's some different things to think about with this. I said sometimes these things can do the greasing for us, but that does not mean that they take the place of the importance of monitoring the process. And the monitoring of the process should be both for, is it working as designed? Is the battery still have power? Is there still grease in this device to be delivered? Is it getting where it needs to go in the bearing, or something else happening? And then the second part of monitoring the process is about the setup, right? When we set these things up to deliver at a certain rate, monitoring the process, monitoring the performance of the bearings to say, has that been set up right? Because many of these are configurable. Some deliver grease more quickly. Some are intermittent so that we can dial that back. We can change the settings so that we can deliver more grease more often, or more grease less often, or less grease more often, or whatever works to optimize the application. And we really don't know what that optimal condition is unless we're testing the grease, because grease testing will help us say, what is the condition at the bearing? When this is set up and it's running, is it optimized? Is it pushing away the contaminants? Is it delivering new grease before the grease that's already there has aged out, before it has broken down and gotten soft, before it has oxidized and is no longer a suitable lubricant? So grease sampling and analysis of the grease in the bearing, or the grease that's being purged out of the bearing. And think about that grease that's being purged out of the bearing, whether that's a manual purging or whether it's from an auto luber like this. It tells a very important story. It tells the story of the last moments of life of that grease before it was displaced and replaced by new grease. And if we capture that sample and we look at it and we ask the question, what's the condition of that grease? Does it still meet its design to protect that bearing? Number two, how much life does it have left when it is being displaced? And that could go by, we can figure that out by looking at the condition of the grease, but also looking at the condition of the additives. And we'll talk about how you can, see those kind of levels in your analysis. Another thing is, what's the contaminant levels in that grease that has just started to leave the bearing? Because if it's not being replenished often enough, it may be that the contaminants are working their way in. So we may have to change the settings. So all this comes about or can be enhanced by using grease sampling and analysis. And so we like to, just talk about that and introduce that as an approach. I did talk about, and this really goes to, setting that up and optimizing those delivery frequencies and quantities. Okay. And, this chart here kind of shows different approaches. And one approach that some folks will use, and I'll tell you, it's much better than the historical of, I just kind of walk out there every so often and I add some grease. But when folks start using ultrasound as their primary and only tool to decide when to add grease, understand that the ultrasound levels stay low as long as a lubricating film is provided. The ultrasound levels go up when we lose that film. In other words, we have to starve the bearing to know it's time to add more grease. And so you get this constant cycle of bearing starvation and then lubrication, and starvation and lubrication. And again, it's much better than other options that are out there that don't give you any feedback to the process. But certainly we can get even better, especially for our most critical machines where we want these grease lubricated components to last a long time, to have little wear, and to get the maximum return on what we've invested in those assets. For those, we can do better. We don't have to wait for the grease lubrication to be depleted to lose the lubricating film to know about the condition of the grease if we use grease sampling and analysis. And that's why it becomes perhaps another step in the process to get a little bit better, because like I said, when you're using the ultrasound, you're looking for that loss of lubricating film. You're looking for the interruption of that EHD or elasto hydrodynamic lubrication that separates the metal surfaces. The way I see it, ideally, we never lose that film. We always maintain that separation, and we do so by, number one, where we started today, which was choosing the right grease for the application, which includes a base oil that has the right kind of, kind of base oil with the right viscosity for the application. And then secondly, using grease analysis to understand when it's starting to degrade. And that degradation could be oxidation. It could be loss of antioxidants. It could be breakdown of the thickener. It could be because contaminants are getting in. It could be because the wear rate is starting to increase. So all those different things, the wear, the consistency changes, the presence of contaminants and oxidation, you'll find are at the heart of grease analysis. And grease analysis answers all those fundamental questions about bearing grease lubrication. Is it being done properly? Is it being done in a manner where grease gets replenished in a timely condition to help protect that asset? And ultimately try to avoid like these bottom photos where we have loss of that lubricating film, asperity contact or surface contact, and the ensuing damage that can occur. Now, we did talk about other types of situations when it comes to grease, and the question about should we really be using a sealed bearing? Should we be worried about adding grease? Does the process of adding grease periodically create its own set of problems? Grease is helpful to a bearing if it's the right stuff. Grease is helpful to a bearing if it's the same grease that's already there. Grease is helpful to a bearing if it's not already contaminated. And so those three things are actually a big part of, problems that get created by greasing. Over lubrication and under lubrication, both major causes of failures. And that is that we're not getting out there and greasing often enough, or delivering grease to where it needs to be, or in many cases, just adding too much grease and it has nowhere to go, and it creates secondary damage in the machine. So that quantity and delivery can be problematic, and we can induce or cause failures by greasing machines. Another thing could be that there's already a grease in there, and we add a different grease, and now those greases are being mixed together. And this happens when we relubricate. Sometimes we get a brand new machine and it comes already greased, but that's a product that we don't even have in our facility. So we take another product and we start to pump it in, and then you get the incompatibility. And that's a major cause of grease lubricated component failures, where you have two different grease chemistries coming together that are not compatible. Then the result can be a few things can happen. Sometimes grease just hardens up. It gets very hard. It creates resistance to movement. It overheats, creates torque, and all these issues. In other cases, the grease gets very, very soft, or even separates, where you get the thickener and the oil comes out of the thickener and runs out of the machine. You'll see this sometimes. You'll go up to a grease lubricated machine and you'll see oil dripping out. And someone will look at that and say, oh, it must have overheated. Not necessarily. That separation of the oil from the thickener is often a telltale sign that you've got two different products going together. So that was one thing we said was about the amount that we add. Is it over lubricated, under lubricated? The second being the mixture of incompatible lubricants. And the third being, who's to say when we get new grease, or we get grease in a grease gun, or we put grease in an auto luber, that's clean? I mean, we talked about wanting to add grease to keep contaminants out of the bearing. But what if we're introducing contaminants with the new grease? We kind of know that from the world of oil, right? We test new oils and sometimes filter them to reduce their particle counts, because we know the particles in oil can limit the life of that component, can cause damage. Well, what about grease? Is the grease clean? Is the grease dry? Because if it's not, it can limit the life as well. And so that's another thing that we can look at. So these three different problems that we can introduce by greasing, which are the wrong quantity. Okay, that one I'll hold aside for a moment. But putting in the wrong grease for incompatibility and putting in grease that has contaminants, they can be measured by grease testing, so that we can monitor that. The quantity can be a different issue. When you're over lubricating, that can be very much a function of just not having feedback to your process and so on. But a lot of that can be determined. A lot of those causal factors can be determined by grease sampling and analysis. Now, there's plenty of environments where it makes sense not to introduce this idea of regreasing, that more problems can be caused by regreasing. And typically that's going to be where you have slow moving machines, lightly loaded machines, machines in very, very contaminated environments. The decision may be made to go with a sealed bearing, seal out the contaminants, seal in the grease. Don't create these failure mechanisms of somebody putting the wrong grease in, or too much of it, or not enough of it, or introducing contaminants, or mixing greases. Just go with the seal bearing. And that may be the right decision, but realize when you choose a sealed bearing, you have limited the life of that bearing to the life of the grease. And the grease life is always going to be less than the potential life of the bearing. So you're kind of giving up on what you could be getting from that bearing. And as long as that's all right, it may make sense. So, here we introduce the difference between a sealed bearing and a shielded bearing. Very similar, very difficult to access, almost impossible to do grease sampling and analysis with these kind of bearings, unless your grease sampling and analysis is a component of failure analysis. And if you have a failed bearing, this is a great opportunity to learn why it failed. And too often bearings are just thrown into the rubbish bin and said, well, it was a bad bearing, or the grease was bad, or something, or it was very dirty, or there was clearance. And none of those conclusions help you understand why that bearing failed. And so, in the lab that I work in, failure analysis is an extremely important part of the service that we can offer to asset owners to help them understand, why did that particular bearing fail? What is going on in your process, your operating process, your operating environment, your maintenance activities that led to this failure? And so if we can make that determination, if we can help them understand, was it a mixture of lubricants? Was the grease dried out because it hadn't been replenished? Were we at the end of the life of a seal bearing? Was the seal compromised? Were contaminants present? Was there an abnormal wear pattern? Does it look like there's misalignment involved? Was there overloading taking place? Was there excessive heat? Was there a fit problem with the bearing? All these things can be determined. So in this workshop, we'll get more into understanding shielded bearings and sealed bearings, knowing when to decide to use one or the other, knowing that there are limitations then in sampling, but knowing what we can and can't do with that. So why do we analyze grease? Well, we want to avoid things like this. Wow, this is a pretty wild bearing that I stumbled upon one day. And there's just a huge clearance here because basically the bearing is all but gone. The rolling elements are gone. They're ground into dust. And you can see the red arrow there showing you the what was once a combination of grease and balls and cage material and so on. And astonishingly, this was still turning when I saw it, but it wasn't going to for long. So there was a huge opportunity to see the things that led to this failure a long time before it got to this point. And that's what grease analysis can help us figure out. When we look at things from a root cause failure analysis perspective, we sometimes see this, it's just a mess, right? We've got so much damage taking place here. And sometimes it's amazing to think that machine continued to run up to the point where it was able, where it was looking like this. But there was a lot of opportunity to identify this. Sometimes just to catch a failure in progress earlier, but even more importantly, understanding that failure. Sometimes being able to intervene, right? So if the start of a failure is a contaminant or the wrong grease being added, if we are taking samples and analyzing them and looking at them often enough, we may be able to intervene early on. We may be able to take out the bad grease. We may be able to flush grease. We may be able to flush contaminants. We may be able to improve the sealing condition, and remove these causes of failure, and perhaps eliminate failure altogether. And sometimes we find systemic problems, issues that not only affect a single failure, but if we understand that they're happening, can affect other assets with that company, with that customer, in that organization for that type of component, whatever it happens to be. This is it's a picture that you see quite a bit, which is grease getting into the windings of an electric motor. And the grease is spreading around and is obviously doing damage there. It's damaging those windings. It's coating them from a heat transfer perspective. That's been affected, and we've compromised the shield in this case. In my organization, we had a similar kind of motor that we investigated just this past week, and in that case, not only did the greasing process damage the shield, but cause that shield to be forced into the bearing and destroy the cage. You could see incredible heat being generated because the shield of the bearing stalled the cage. It actually held the rolling elements in place so that they were no longer rolling. They were sliding elements. And the heat that was generated there was just phenomenal. And so it causes this huge degree of damage and failure because the greasing practices are not correct. In that case, there's the shielded bearing, like I had just shown you here a moment ago, and I'll show that again, where you have this metal shield arrangement, and yet there was still a fitting that allowed them to add more grease and provide so much grease that the pressure collapsed and forced the metal shield into the bearing, causing that failure. So sometimes you've got a perfectly good operating piece of equipment, and the greasing itself is the cause of the failure. Now, I like to share this one because it does talk about the consequences of poor practice and what can be discovered with grease analysis. And this was a bearing. This is a pillow or pillar block bearing, as they're described. This one here is completely damaged, obviously. And you see this reddish dust. This failure came about due to grease mixing. Two different kinds of greases put together, causing the oil to run out, causing there to be metal-to-metal contact and oxidation, which is what you see here. And know that when this first started, there was this opportunity to see that. There was small little oxide particles showing up, which would change the color of the grease, and that could have been detected. And then the ferrous content was increasing, right? So there was that chance to see the amount of ferrous debris increasing as it was sampled. And then, by detecting the grease itself, seeing elemental and bond type things that we would see in an FTIR analysis that were not characteristic of the grease that was supposed to be there. So evidence of mixing. And I know that grease analysis could have helped us avoid this failure because it did help us avoid failure of 19 other similar bearings in that same facility, because we then, after this failure, were able to take those samples, look for signs of mixing, and for the ones where we found that mixing, we were able to purge that out and save those bearings and prevent failure. So that's really what we're talking about here is, what can we do to understand these mechanisms and try just to improve the overall performance. I mentioned that this workshop is going to go into the evaluation of these grease test stands. One of them here is about relubricating a shielded bearing. And so you can see we had various test stands here. We set up different orientations, horizontal and then vertical, like you see here, to see how the grease flows. How does the grease move through a bearing enclosure? How does it get into the bearing? What happens to the grease that's already inside of that? Can it get through the shields? And, we set up these test stands and then pulled them apart and analyzed the greases and learned a lot about that in the process. And those are the kind of things that we can share about, things like relubricating double shielded bearings and what happens to a pillow block bearing when it gets relubricated. How does that change its temperature? How does it change the ultrasound measurements that we might make? Some of the other test stands these were motor operated valve test stands where this is a grease lubricated gear. This is a worm gear. And so, what do you find inside of that? And can that be sampled? What happens when things change from an alignment perspective? And we find that the wear levels change. So there's a lot of background information here that helps us understand the opportunities that are there for grease testing, for grease analysis, grease sampling and analysis. And so we share that with you in this class. We share with you some of the research that was done that helped say, what's the value of grease analysis? But maybe even more importantly, before we get to grease analysis, is what about sampling? how do we get a representative sample? What tools can we use, and so forth. And so we introduce things like the grease thief and the different versions of that allow you to pull and extract a sample. And that's a key difference between oil and grease, which is that oil tends to want to circulate through a system, which means that it is being distributed. It gets mixed by the movement within the machine. And as long as we go to the right spot in the machine to pull out that sample, we end up with something that tells the story, that's representative. And that's always helpful. But grease is different. Grease doesn't circulate in the same way. It does circulate. And we're going to share with you some videos and some things that show how grease behaves. And it's really sometimes quite surprising how grease can move and behave. And we do that by taking machines apart and then watching what happens inside. And we'll share that with you in this workshop over the next few days. But when you understand that, you recognize that it's not happening everywhere. And some grease is it tells you that story. Some grease is right there where it's actively lubricating the component. So other grease in a same enclosure may not be. And this is the real challenge in getting grease analysis right, because if we don't focus on getting that representative sample, we may end up with a sample of grease that doesn't tell the story at all. And the problem is that we can send that to a laboratory and say, tell me what happened here, and it has nothing to do with the condition of the machine. And there's a big disconnect. And I know that because when I first started doing grease analysis, which was, well, I have to admit now it's over 30 years ago, I first started doing grease analysis. And the first time I did this on a large scale, it was a complete failure. It was a complete failure because I only focused on the analysis piece. I didn't look at the sampling. I trusted that the samples that were brought to my lab were what I needed to look at. And the truth of the matter is those samples were random. They were from grease that was, in some cases, doing the work of lubrication. In other cases, it was just the grease that was convenient to pull out of the machine. It was the grease that was close to an opening plug or something like that. And so I spent a lot of my time doing analysis on samples that were not valid. And so when we set about to come up with a solution, we knew it had to be both the sampling solution and the analysis solution. And that's what you see here in the grease thief. And so in this class, we'll talk about, the design of these sampling devices, talk about the options that are out there, the differences between them. The fundamental difference that there's two different kinds of grease thieves. One has a stinger probe on it, like you see on the right here. The other one does not. And each has its own usage. And so, I'm going to get into, showing and sharing some of that. I've got along with me, some of the tools like the T-handle that you see here, which is adjustable, allows you to go into the machine to a certain depth and target that grease that's going to be representative and tell you the story of what is going on there. So so I'll head back aside. So, understanding those sampling devices, how they're used, and how to use these various kits, the kits that are available. And we'll go through and explain what's in a pillow block kit. When would you use an electric motor kit? And it seems obvious, right? Well, for electric motors, not actually. Sometimes the pillow block kit's the right kit to use for a certain style of electric motor. In other cases, it might actually be the MOV gearbox kit. And so we'll talk about how you sort through, and choose the right kit for the application. We'll talk about, things that got developed over time, like the Slim kit, which was in response to, hey, there's machines out there that are just too small of an opening to use the grease thief. So we'll talk about, what those other options may be. Different specialized applications like robot sampling, right? These especially in Asia, the robots tend to be grease lubricated. Some of the European robots are oil lubricated in their joints. We're talking about the grease lubricated joint robots, which are really, the growth there is substantial. So if you're either an asset owner, you're in the manufacturing process, or you're a laboratory looking at using grease analysis and offering grease analysis, robots is just this huge potential to leverage what grease analysis can do for us. And it's a very straightforward process. And these robots use the grease that they use is pretty expensive, but it's light colored. And it really presents itself well for analysis. And so we'll talk about the tests you can do, some simple screening tests and so on, and just kind of go through the whole process of how we choose the right kind of kit, the right kind of sampling methodology. We'll share the different techniques. I'll do some demonstrations. I'll be broadcasting from our laboratory later this week. And in our laboratory, we have more than just the instruments and so forth. We have test stands where I can stand over, a typical machine and actually take a sample live to show you how to do that. And so we'll take advantage of that throughout this week coming up, because it is so important. And whether you are the asset owner or whether you're a service provider or you are a laboratory, nobody in this process wants to get stuck with data that comes from analysis from bad samples, from samples that aren't telling us what's going on in the machine. It doesn't help anybody. And really that has to be integrated into the solution that we have for grease analysis. The sampling part has to be addressed, on the analysis side of things, there's when we set about to come up with an integrated solution that addresses these sampling challenges, but also, is part of the analysis process, the recognition was there that we can't rely on what maybe has been historical grease analysis, which is get a really large sample of grease and take it into the lab and try to dissolve it and do other things so we can use the oil analysis equipment that we have. It's not going to work. And in fact, the demand that laboratories sometimes put out there for grease quantities, which is fill up a 4-ounce or 120 milliliter sample bottle with grease and we'll analyze that, it's just not realistic, because a lot of critical grease lubricated components, when you really look at, even some larger bearings, when you really look at what grease and how much grease is actively lubricating it, it's a small amount. It's a tiny amount. And to ask for 100 grams of something may force that person taking the sample to add more grease to get to 100 grams. So now you're not analyzing the grease that tells you the story. It's already been diluted down with enough grease to give you the volume you need. So it really needs to be focused on a very efficient use of a very small volume of grease. And I think it helps if I, for those of you who join us today who aren't really that familiar with the grease thief, it's just to pull one out to share with you and to show you here. Yeah, I'll just show you this this sleeve here. This is one of the sample kits, and it comes in a sleeve that's sealed here, and I'm going to open up that seal to access this opening. And down inside here is the grease thief, okay, with a cap on the end. And you can see that piston in there moving back and forth. It's more than just a few pieces of plastic. It's a very significant design here. And that piston is a precision fit within the bore of this inside there. It has a precision fit. And that's a really important function for getting that sample, because what it allows us to do is not only, use the threads that you see here to thread it into the machine and allow the grease just to enter and push it down. That's one way to get the sample, but also to use it in a tool like I showed here, where it can be held in place and take that sample. And then this 1 gram is what we're going to go ahead and take that sample with. So what you see on this screen is this small, 1 gram sampler going through this process. And we'll share with you, and I'll demonstrate later this week, putting that grease sample, once it's in that container, right into this ferrous debris sensor. And I'm going to share, this is exciting. This is some new information that we have on this device called the FerroQ, which is taking advantage of some of the technology that's coming along today on sensors. And everybody's heard about sensors. The sensors are coming, and we can put, whether it's vibration sensors or whatever, but we can take oil sensors and put them onto the machine, this whole industry 4.0. And some of this advancements in sensors has allowed us to partner with a company called Poseidon Systems that has a really advanced design on measuring ferrous particles in oil. And we've taken that design and made an instrument that allows us to accurately represent the wear levels in grease. And the challenge there is that when you have a grease sample, those particles can be different sizes. They can be distributed differently. If we have an oil sample, we're used to shaking that sample up and mixing it up really good and then distributing that evenly, but you can't do that with grease. So again, and I mentioned this before, there's differences between grease and oil. There's differences in how we have to go about getting the sample. There's differences in how then that sample presents itself for analysis. And one of those things is the distribution of the things that you're measuring. So this is a great device that helps us to get a repeatable and reproducible value that gives us the chance to trend ferrous wear levels in greases, which is really fantastic. It's quick, it's easy, and it gives us that insight into the wear condition of the component. And then, the next step in this process is this grease thief analyzer, and it's a tool that allows us to look more closely at the consistency of the grease. In other words, how is that changing over time? And the consistency historically has been very difficult to measure, but we're going to show you, and that's where Richard's going to demonstrate that at tomorrow's session on how you can use the grease thief analyzer to get those measurements, to measure them over time, to see how they're changing. Is there separation of the greases? Is it getting hard? Are the greases hardening? Is it drying out? Has it softened? Has someone put the wrong grease in? And all of these things that can influence that, because the reason we use grease is because we want it to stay in place. And that ability to stay in place is its consistency. And so we need to measure it over time to make sure the grease is continuing to do its job. And then you get this extrusion process. And again, we're going to show you this live, and you can watch it happen, and it's really neat to see for those who haven't seen it. But it takes that small amount of grease, prepares that as a thin film, and gives you a chance then to do more with it, up to 10 different tests. And so we'll get into that and share that with you. If you have that full sample, you're good to go with like 10 different tests with this consistency, contamination, oxidation, wear levels, even doing analytical ferrography, looking at antioxidant levels, and so on. But what if you don't have that much sample? And sometimes you don't. And one of the case studies I'm going to share this week is around helicopters, military helicopters, where we looked at that very closely. And some of those locations really did not have very much grease to go after. 1 gram of grease doesn't sound like we're asking for a lot, but sometimes that's just more than's there. And we actually came up with some really small volumes, basically down to about 1/3 of a gram or 0.35 grams of grease. We were still able to run a number of tests that helped us to understand what's going on. So we'll talk about that. We'll share this FerroQ device and its ability to measure up to 200,000 parts per million ferrous debris, which sounds crazy to someone who does oil analysis, 200,000 parts per million. But astonishingly, in some grease lubricated applications, and it's because, again, understanding differences between greases and oils, that the particulate really gets concentrated. Where particulate gets concentrated, because it doesn't get filtered. It doesn't settle out like it would in an oil reservoir. It's there and it accumulates over time. So we can get fairly high levels. So having devices that are designed to measure these higher concentrations that we see in grease is really important, that we have the right kind of equipment to measure the grease. That's not to say you have an oil analysis laboratory, you push all that equipment to the side and have to get all new grease analysis equipment. No, in fact, for a lot of the testing for greases, we can leverage that existing oil analysis equipment and utilize it after we prepare the grease sample in a way that optimizes those oil instrumentation devices. But there are other measurements where grease is different enough that we do have to have a targeted solution for that, and this is one of those examples. So we'll look at that. We'll share that. We'll share examples. We'll do the demonstrations. We'll share the data, and the data that you get out here out of doing consistency measurements. Here's 3 different grades of grease: a grade 1, a grade 2, and a grade 3 grease. And you can see that the load profiles of these are quite different. And that's what we're comparing. We're looking at, the changes within a certain grease and then how that changes over time. And it can help us too to diagnose. And we'll get into what do you do with the data? Like what's the story that the grease analysis data is showing you? Well, you can have a normal profile where the baseline of the grease is very similar to the sample that you're checking. You could have hardened grease samples where you've got grease drying out. You can have softened grease, which could be from excessive working and shearing of the grease. It could be from mixing. It could be from contaminants. And then even unusual data signatures like hard particles showing up in the grease. And so that's part of what we're going to share with you this week is, what kind of data is out there? What do I do with it? What kind of story is it telling me about the grease? And how do I translate that into either, if I'm in the laboratory, recommendations that I can make to the asset owner, or if I'm the asset owner, what do I do differently? How do I respond to that data? How do I address the immediate things that I'm seeing? And then how do I change my practices to make long-term improvements to the performance of my equipment, maybe even optimizing, how I use grease, how much grease I use, how I add it, but ultimately getting that return on investment that's so important to demonstrate, to justify the resources it takes to do grease analysis. And so we'll share, this data with you and how it's used. We'll show you, some improved methods. This is an older device that some folks might recognize that you can use to measure colors of patches for varnish testing and things like that. But it's a device that's kind of obsolete at this point. So we've come along with some newer technology that allows you to measure grease color in addition to some of those other things that we would use that for, but using a very, very small sample of grease and being able to get a measurable representation of the color profile, which is really a Beer-Lambert law, if you're familiar with that methodology, to evaluate changes in grease, contaminants, oxidation, and just the accumulation of particulate. And so we'll share that with you. Share with you how color, for instance, changes over time. And some of these things are pretty obvious. And one of the reasons that I have been studying color in greases is because early on, when people would send me grease samples, I would get comments like, "I'd like you to analyze this because it just doesn't look right." And there's something in that. When an asset owner can perceive changes, when they can say, "This doesn't look right to me, this doesn't sound right," this seems too hot, or it's vibrating strangely. Don't dismiss that. There's something to that to someone who understands their assets. So if we can validate that through measurement, if I can take a measurable quantity of the appearance and relate that to changing conditions, that's really going to help someone who says, I think I'm seeing something unusual here. I need to get a numerical representation of that. I need to know what to do next with that, and see what that tells me about the conditions that I'm seeing. And so that's color. So, other tests that we were talking about here, we'll also mention about rheology, which is really an advanced way of looking at changes in the flow characteristics of grease. Something that's familiar to folks that do oil analysis is analytical ferrography, right? Which is just looking at the wear particulate and really sometimes other particles. Well, we can do that for greases as well if we prepare it properly. And some of the same stories can be there to tell us about, is it normal wear modes, abnormal wear modes, and so on. And so that's the kind of data that we try to extract from a grease sample given these tools and so forth. And then, over time, we also want to talk about case studies. And some of our case studies are specific to different industries, like wind turbine industry, which is a huge and growing area for countries all over the world. Asia is definitely no exception. There's a lot of Asian countries that are adopting wind energy and have significant and ambitious programs in that area. And so we've been fortunate enough to be involved in some research projects. These pictures came from Denmark, which is really a kind of a starting point for a lot of the wind technology that's out there. And so by understanding what's happening, understanding how grease behaves in these bearings and so forth, helps us develop sampling tools and analysis techniques, and really the interpretation of the data. We looked at our first wind turbine almost 10 years ago. And so it's that accumulated data, knowledge, and interpretation that we want to begin to share with you as part of this workshop. What do you do with this data? What does it mean? What's the significance of it? What kind of story is it telling me about what's going on inside that particular component? Is there a possibility I got a bad sample? All of these things factoring into it. How reliable is the data? Am I using the right kind of analysis? And is there correlation there? And so we're going to share, those kind of things with you over time, which over the next few days, which help to understand that a little bit more in things, again, like wind turbines. Sometimes you even see differences in performance of greases. Now, I want to caution that, because the kind of testing that we talk about isn't really meant to be performance prediction. It's not like, hey, here's two different greases, tell me which one's going to work better. Well, the answer to that is it really depends on the application. Which of those two greases is the better suited for the application? So you can't kind of generically say that grease A is better than grease B. But if you have multiple assets that happen to be that are similar, that happen to be using different greases, sometimes you can look at things like, how do they soften? How does the antioxidant packages hold up? Where are the wear levels on these different components over a period of time? And does one grease seem to protect better than another? And in those limited studies, sometimes that can provide some insight as well. In addition to wind, we'll talk about robots, how you go about looking at the data to find what an outlier is, how to establish action criteria for that. What that really is telling you in the long term. Things like simple pillow block bearings, and sometimes where the data can lead you astray. Like, I look at this graph here, and it really seems like the two results to the far side of the graph, to the right side of the graph, must be the components that are the most damaged if we're looking at wear levels. Further investigation shows that they really weren't. They just weren't being greased or re-greased at the same frequency that the other ones were. And this really goes to a big difference. Again, another difference between oils and greases is that when we look at the values, like for instance, for wear or contaminants that we see in a grease, and I think it's more to do with wear, is that it's very important to understand how much time has elapsed. And if I have two samples and one sample, maybe ran for 3 months on the grease and the other sample only ran for 1 month, even if those machines are wearing the same, they're not going to have the same values. So we're going to talk to you some more about how you have to almost normalize your data when it comes to grease wear levels, and make sure that the comparisons that you make are valid. And so part of that goes to understanding maintenance practices and operational practices of these assets. So it's a layer of complexity. But if you don't factor that in, it can be a little deceiving when you share results with asset owners. So other things that we want to talk about, okay, I did show and mention that one here. We will get into some of the setup and utilization of the Grease Thief Analyzer itself. And I think there'll be two reasons why this may be of interest. And one is to people who own the technology, just so that they're able to see, and continue to learn kind of in this continuous learning environment, what that shows you, how, what kind of changes have been there in the technology, and what all you can get out of it, and what to do when things aren't expected. That could be one thing to consider for existing owners. Another could be people who are just new to this. They're just a little curious. They want to see what's going on here and try to find out, is this something that we should be doing? Should we be testing greases? Should we be measuring the ferrous content? Should we be looking at the color of the grease? What are our options there? And so by sharing some of the technology and the instrumentation in its use, that may help someone better understand the capabilities and make a decision about getting involved in that. And another could just be for folks who are more on the asset owner side of things, to better understand what laboratories may be out there doing today. And so, I've got a number of people have joined us today, and some of them are, they've been already doing grease analysis, like the folks at Running Land Labs in Shanghai were actually one of the earlier adopters of our technology, and they've had the grease analysis capability for several years now. And so, someone who is in that part of the world may be thinking, okay, I want to know more about this because I want to know what a lab like Running Land Labs would be doing for me. And they're one of the labs that we've got laboratories in Spain with Grease Thief Analyzer, in several areas in North America, including Canada. We've got them, just it's spreading and it's growing. Poland, in Europe as well. So so it's out there, and this is something and I think we're going to see more of that. We've got other practitioners out there that are finding out more about it, laboratories that are looking at this. So from an asset owner standpoint, it's like when I see this and I see this option, I maybe want to understand what's actually being tested here. What's the data that I'm getting, and how is it being derived? And so that's another aspect that from sharing this that someone may come away with. So we'll talk about troubleshooting the equipment. We'll talk about the whole order of the process that I shared earlier, which was, you get the sample, and then, maybe start with the ferrous analysis. And then from ferrous analysis, you're going to maybe to color analysis would be the next step, and then from there, you're putting it into the Grease Thief Analyzer to do the dye extrusion. And, I didn't mention it here, but you're going to see that tomorrow when Richard Janoski shows us the particle counting, right? So I did mention about, this whole idea of contaminants and how contaminants can make a big difference in the life of your equipment. Um, and, you know, it's one area that we don't have a lot of insight into often. And if you think about the way grease is, it's tricky to see whether it's contaminated. If we have an oil sample, we take an oil sample and we let it sit on a shelf for a while, maybe come back a day or two later, we look at the bottom, we might see a little ring of dirt at the bottom, or we might see haziness there and see moisture. But the challenge is in the grease, you don't see those things. Grease can be very, very dirty, and you can't see it because those particles are held in the matrix of the grease, or they don't get cloudy in the same way that an oil sample does. They'll have the same effects of light when we look at it. So it becomes even more important to have ways to confidently measure the cleanliness of our greases. And most of what I've talked about today, and I've talked about, grease selection and, just other, adding grease and auto lubers and things like that, just good grease practices. But also when I'm talking about analysis, a lot of this has been focusing on analysis of used samples. But the other part that's here, the other potential that's here is in new grease samples, is that I could look and kind of confirm that the consistency is where it's supposed to be, especially if it's been stored for an extended period of time. Secondly, what's the moisture level? What's the particulate level? Because I'm going to handle that grease. And, I may put it in a grease gun. Well, what if the grease gun was dirty when I started? I have no way of really seeing that. I mean, I might see obvious dirt on the outside, but what about the little particles, the microscopic particles that'll do damage to my bearing? I can't really see that. So what you will see tomorrow in tomorrow's session, the second session number 2 tomorrow, is Richard Janoski showing you the Grease Thief Analyzer, not only this dye extrusion process, but when this plastic substrate continues down the line, there's a microscope there. There's a high resolution microscopic camera that looks at this thin film of grease and sees and identifies the particulate, and it sizes it. So you have a measure of cleanliness, of grease cleanliness. And I can do that for my new greases. And here's, as we get to the end of our session here, and this is our, the end of our free time, if you will. And hopefully a number of you will join us for later this evening, for later today and tomorrow and Thursday to continue this discussion. But, as we get to the end here, I want to kind of leave this idea is that we can't just assume because grease is new that it's clean or dry. And I'll give you an example of that, is that we had grease samples that were sent to our laboratory, and they were sent by a grease manufacturer on behalf of their customer. The customer is having some issues. And they say, can you look at this grease and tell us what you see here? And we took the grease sample, we analyzed it, we found very high wear levels, so we looked at it under the microscope using analytical ferrography and found evidence of gear wear, characteristic particles that of the sliding variety, thick platelets that come from gear wear. So we communicated to them that we saw a significant amount of gear wear in the grease sample. And the response was that, well, you mustn't know what you're doing. This wasn't even from a gear, it was from a bearing. And we said, well, give us one more shot at this. Can you send us, you're the grease manufacturer, send us a brand new tube of the grease so we can just background this as a reference. And we did. And don't you know, in that brand new grease, it was full of gear wear, because in the manufacturing process, they transfer the grease using gear style pumps. They had a bad gear pump in the grease manufacturing facility. So every tube of grease that they sold was full of particulate from that failing pump. And it just kind of underscores the importance of monitoring grease for overall to understand, the long-term life of our equipment and trying to get the most out of the grease. Another case study that I'll share with you comes from the military helicopters that I spoke about earlier, where we did over 1,000 samples of this fleet of helicopters on different locations across the frame of it, and created a 7-parameter study where we looked at 7 different things about the used grease samples to evaluate their condition, with an eye towards answering this question: is the current practice optimal? Okay. Is the current practice of taking that helicopter, that asset, out of the field, putting it into maintenance and replenishing the grease and then sending it back out again, is it optimal? Is it often enough? Is it being done the right way? Is it addressing the failure modes which are there, which include moisture getting into these components, particulate like sand, for instance, okay, dirt getting into these components, for the wear levels, from the condition of the grease, okay, the consistency of the grease, the oxidation, the aging, and the end of the life of the grease. So we looked at these 7 parameters. And when we evaluated them, we looked at each different component on that helicopter and determined what the optimal number of operating hours would be to replenish the grease, to make sure there wasn't high contaminants, to make sure that the grease hadn't oxidized, to make sure that the working of the part hadn't changed the consistency of the grease. Remember those 4 things that we talked about: wear, consistency, contamination, and oxidation. We looked at those 4 categories in these 7 parameters. The result of this was that we took the existing, and this is 50 years of maintenance history. 50 years of maintenance history had gone into developing that greasing interval. We took that and we were able to adjust that. And the result was that it doubled the amount of time, amount of flight hours that those helicopters were able to stay in the field, because certain components were being over lubricated. And it reduced the maintenance workload by over 40%. So when they finally did have to come in for maintenance, it was 40% less tasks being done from a greasing perspective. And in doing so, we actually improve the safety and the life of the components by having the grease analysis data there. But it was estimated that this was going to be over $10 million savings per year. So, you know, for a fairly small investment in grease analysis. And it's those kind of examples that we want to be sharing with you. Again, whether you're that asset owner or whether you're a service provider trying to help people get better performance out of their grease lubricated assets, or you're a laboratory or someone that's looking at starting some capabilities at a laboratory or even a mini lab level, this is the kind of information that we can share with you. Our 10 plus years experience in developing this technology, we want to share it with others. So I want to thank everybody that joined us today to get this initial overview. I want to go back right now to share with you this slide that I started with that went through the different sessions. Of course, we've completed now session 1 on the first day, and we'll be coming back in a half hour. If you have not signed up, please use this enroll to sign up and to have access to log in, and we'll look to join back with some of you here for our second session. If you can't join us, we understand. We hope that this was helpful. I will be putting this a recording of this first session on YouTube so others can see this and so forth. But we hope this is the first step towards being able to answer some of the questions that you might have about grease sampling and grease analysis, greasing in general, so that it can really help folks do a better job with their grease lubricated assets. So thank you very much. Feel free to reach out to me, and I hope I get to join more of you in a half hour after we take a short break. Have a good evening, and take care.